Today we're going to start to introduce the normal distribution, which is actually something that you've kind of seen before. This is a different way of using the normal distribution. It comes up in all sorts of different things, but when you hear about flatten the curve, right, you see something that's in this type of shape, and this type of shape actually models how diseases can spread, right, where it grows exponentially, it starts to level off, and then it would start to decrease, the rate at which people were getting the disease or just the overall people that still had the disease. When we talk about flattening the curve, that curve still has the same basic shape, right? But you're going to flatten it out this way so that it looks a little different. And it's not the best picture, obviously, as you can see that I drew, but it's still the idea that is this normal curve shape. The way we're using the normal curve is for distributions of data. So if you remember, we did frequency tables yesterday, and if you remember back to 9th grade, you can take those tables and you can draw bars for however high those frequencies were. And maybe you take data and, I don't know, you get a histogram that looks something like this, right? So this is kind of up and down and random. The idea of the normal distribution is that we have all these little bars in here and we flatten them out to a curve, different type of flatten, right? Flatten, so we're kind of flattening off those corners. But if we did draw in that whole histogram, we end up with a very symmetric histogram, okay, where we have a lot of values in the middle, bunched up, and then less and less to both sides, and both sides look pretty equal. And when we're talking about the perfect normal distribution, which actually is a pretty interesting equation to make this graph. It involves E, it involves some other stuff. We're not going to look at it right now. It actually has a pi in there, which is kind of crazy. But basically this curve, if we talk about standard deviations, so if we go one standard deviation out in each direction and it's a normal distribution, there is always 68% of the data there. In our example yesterday, we had 75, okay, kind of close to 68, but that wasn't a normal distribution. When we go 2 standard deviations out, there is always 95% of the data. And when we go 3 standard deviations out, we have almost everything. That's 99.7% of the data. So we're going to be using this normal curve. There's actually something on the calculator that calculates it for you, but we're also going to be using pictures because it's really kind of important. If you ever move on in statistics, if you were taking this course in class, we would do a lot with the shape of this curve and how it works. So let's look at that first example, and I'm actually going to go into Delta Math for the example, but I do have the work here too. So our first example says, at a customer service call center for a large company, the number of calls received per hour is normally distributed with a mean of 150 calls and a standard deviation of 20 calls. So that means throughout a day, and if you keep collecting how many calls happen per hour, if we draw this normal curve, the average, which always goes directly in the center, the average is also the median when there's a normal distribution, is 150, okay? The standard deviation is 20, so if I want to model this, if we go out 1 standard deviation on the regular normal curve, you'd see a 1 and a -1 here, okay? We're going to write those values which involve adding and subtracting the 20. So we're going within 1 standard deviation. So if I add 20, I get 170, and if I subtract it, I get 130. Next, we're going to go out another standard deviation, and usually we label out 2. That's kind of our general. So if I add the 20 again, I get 190 out here, and then if I add another one, I get 110. We could go one further to do 3 standard deviations. That's fine. If you look at my picture, it doesn't look perfectly symmetric, but the actual normal curve is. So we want to find what is the probability that during a given hour of the day, there will be less than 119 calls. Now, another interesting property of the normal curve is that if we could think of this as a shape, like all this space inside here, I don't want to shade it in yet, but everything under the normal curve, the actual graph, the area of that space is 1. So 1 goes with 100%. So if we can figure out how much of the curve is shaded or how much shaded, that also gives us the percentage or the probability in this case. So I'm going to draw that. My 119 would be right here. kind of somewhere, almost right in between the 110 and the 130. And we want less than that. So if I look here, right, this isn't too much of my curve, right? The taller, bigger part is shaded in. So I'm going to expect a probability that's not super big. Now, nicely, once again, we do have a statistics calculator feature here. You could also do this on your graphing calculator, but this is easier since we're already here. So I'm going to pick the statistics calculator. We're in a completely different part. I'm going to see if I can leave part of my picture, but I'm going to erase this part where I was circling stuff. So I'm going to go here, click on the edit lists, and this is a distribution, normal distribution specifically. We're always going to be using normal CDF. Don't even worry about the other two. Now, this one's kind of weird because I want to find this green section here, right? So the upper for that was 119, if you remember when we were on the other page. So I'm going to go there and I'm going to type in a 119. Okay, so I have a 119. Now the lower is really hard to write in because it kind of goes to infinity if I go, towards that lower spot. So just to pick a number, because we do have to enter some actual number, for the lowers, if I need to go to negative infinity, you could say, I just do negative 999,999. You'll see if you put in a 0, it's really not going to make that much of a difference because this section of the graph gets so low over here, okay, that it's not really much that can fit under that tiny little piece if we're considering that this is kind of like the x-axis. Yes, these two ends do represent approaching 0. There's asymptotes there, don't actually touch 0, kind of going with that exponential function idea we did earlier this year. Okay, so moving on, this mu here is actually another name for the mean. So the mean in this case was 150. So I typed that in. And this sigma is the standard deviation, and the standard deviation that was given that we used was 20. And then I just click the calculate. So down here, my answer, we want to the nearest thousandth here. This is my probability. It's 0.061 to the nearest thousandth. Okay, and that's what I would type in. I would basically just go back to that other page. We'll do that now. And type in the 0.061. So that answer would just go right here and get typed in. Now it doesn't say percent, so I leave it this way. That 6%, 6.1% goes well with my picture where I see, right, that there's not so much shaded in. And I didn't even draw my curve perfectly. It would probably look like even a list if I drew it perfectly. So we're going to move on to our next. So this next problem, at a local restaurant, the amount of time that customers have to wait for their food is normally distributed with a mean of 48 minutes. So with our new symbols, right, we could use X bar, but our new symbol for this that happens to be on this calculator is mu. And our standard deviation, which we know here is just a sigma, is 5. What percentage of customers have to wait between 40 and 52? So I'm going to draw that normal curve just to kind of give me an idea. This isn't necessary for every problem, but the whole point of this is kind of to understand this, even though there is, just a calculator feature that calculates it for me. So average is 48, and so that means average wait time is 48. And some wait times are more than 5 minutes from 48, but on average, you're waiting between 43 and 53 minutes is what this means. So that's one standard deviation away, -5, +5. Another standard deviation away, and I'm not being too accurate here, but that's okay, is add another 5, 58, subtract another 5, 38. That's good. Remember, we could go out that third standard deviation or even more if we wanted to. Our question asks us to look between 40 minutes, which would be somewhere around here, right? And 52 minutes, which would be somewhere around here. So if I shade in this part of the curve and I kind of eyeball, like this is definitely going to be a higher percentage than my last one because I have a whole lot more of that curve shaded in. So we'll go to the calculator piece now. Statistics calculator. and go to our section we want. We'll do a little erasing first just to get this stuff out of the way. I'm going to leave that curve there so I can look at it. So this is a distribution menu, normal CDF. Here I have a really definite low and high. So my low is 40 for this one. My high is 52. My mean was 48 minutes, right? The average wait time. Standard deviation was 5. And I'm going to press calculate. So this one says to the nearest tenth again. And then this one actually says what percentage of customers have to wait between 40 minutes and 52 minutes. And I'm actually going to go back and look at that now. So we'll just get back because I think that's good. And it will throw off your answers and be frustrating. Come on. Hopefully I didn't go back twice. Okay, good. So this one says nearest, or what percentage to the nearest tenth. So I had as an answer 0.7333, but if I want a percentage, right, I have to move the decimal over 2. So to the nearest tenth of a percent, I need to type in 73.3 on this one. And that's just something to check. You know, you guys know you have the two chances, so hopefully you'll catch it that time, but it could be frustrating if you do everything right, but don't type that incorrectly. So we have one more problem we're going to now. So here it says when John runs the 400-meter dash, his finishing times are normally distributed with a mean of 84 seconds and a standard deviation of 1 second. So quick curve. (84), and I mean this is a little bit of a stretch because I don't think run times are usually normally distributed. I would expect them to have some other type of distribution, but not quite this neat. So 85, 86, 83, 82, we'll just write that in. We want to know what's the probability that his finishing time will be slower than 82 seconds. So we have to be careful here though, because slower than 82, sometimes that makes me think smaller, but slower would actually be larger. So we're finding everything from here and up because slower times, as I said, would be more time. So we expect a pretty big percentage heading up towards 100%, you know, not quite 100% when we go and do this calculation. So statistics calculator, go to our distribution menu and, oops, wrong spot, and normal CDF. Do a little bit of erasing here so I can see what I'm doing. So my lower here is 82. My upper, I'm going to do the same thing but positive, so those 999,999. My mean is 84. And my sigma is 1. So when I click calculate, this one just says what is the probability, not the percentage. So I just want straight nearest thousandth. So this would be 0.977 to the nearest thousandth, and that's what I would enter.